Yeah, I think you're going to be good.
All right. Welcome to Compass Wednesday, everyone. It's my honor today to introduce one of my best friends, James Christie. He's a fifth-year PhD candidate in the Department of Atmospheric Sciences, advised by Professor Cassie Gaston. Before coming to Rosenstiel, James got his Bachelor of Science in 2021 in Chemistry and STEM Education from UMass Lowell. Currently, he serves as the MSGSO Vice President. He's on the Dean's Advisory Panel, and he is the ATM student rep. And this week I asked James, if you were in the hypothetical book, Where's Waldo at Rosenstiel, where would you hide? And his answer was on page 72 in crew cabin number 2 on the lower deck of the Walton Smith.
I thought I told you that in confidence.
Today, James is going to be talking about some cool stuff from the lab into the field in his research, his PhD research. Welcome, James.
Hello. So this is the fun moment where I get to talk to you all for 45 minutes, and you have to listen, which makes it even more fun. So today I'm going to talk about kind of the past 4.5 years of research that I've done with Cassie. It's really focusing on the Salt Lake City air quality problem. So if you read the news and like the Midwest or western part of the country, you'll read a lot about air quality degradation in the Salt Lake Valley, specifically in the wintertime. And I'm going to discuss some of the causes of that and kind of dive into how we can mitigate it using some data. So just as a brief overview of the talk, it's kind of split into 6 chunks. It's not going to be as long as it looks, I promise. I'm going to do an overview of the Salt Lake Valley, their pollution problem, and I'm going to go really deep into what causes this pollution to occur. We'll talk about how we measure this N2O5 reaction rate that I've alluded to in the title, and then I'll talk about how we test this reaction rate in the lab in the field, and then finally like a broader, where are we going to go to finish up this research topic in a nice bow before I graduate. I do want to note that this is a very in-depth and niche topic. So if there's any questions at any point, just stop me, ask a question. I'm happy to help because if you likely have a question about my work, someone else does too. So just to help with clarity throughout, I'm more than happy to be stopped and answer a quick question. So to kind of begin, I want to talk about what's going on in the Salt Lake Valley. And to kind of preface why we care about it, the Salt Lake Valley is a pretty fun place. It's 22nd largest city in the country with over 2 million residents, and it's growing quite rapidly as an economic center. It's a major tourist hub with 20 national parks within an hour drive, 4 of the most visited ski resorts, though Kate might disagree with that, and that alone brings in about $5 billion of tax revenue, which funds the city. It's also a major industrial hub with fisheries, the fishery industry being a pretty big export for brine shrimp off the Great Salt Lake. Agriculture and animal husbandry, especially mink farming, which will somehow be important later. It's also a mining, quarrying, and oil and gas hub with one of their major exports, if you live in the northern part of the country, being road salts, which is also going to be important later. And this alone brings in about $13 billion per year in tax revenue, once again, to fund the city. And probably the most important part of this discussion is that it is ranked within the top 10 worst cities for air quality in the world, with that ranking kind of shifting from year to year. And I want to put this into perspective because these 2 photos were taken at the same location, a few months apart, and the view is vastly different. This is a really nice, clean day in the Salt Lake Valley. You can see the mountains in the background, a scenic view. You can breathe the air and not hurt your lungs. And then to the left, we see what a polluted day, wintertime pollution event looks like. The city is fogged over, you can't really see the buildings that well, and you can not see the mountains at all. So the view is completely obscured by this pollutant, which, keep in mind, the residents who live there are constantly breathing during these pollution events. And one big question that is known at this point is, what is this pollution made of? And it's this compound called fine particulate matter, which is shown on the blue line, and about 18 times per year, it exceeds the national air quality standards for 24-hour exposure. That means if you're sitting in there, you're going to be exposed to hazardous concentrations of unsafe and toxic pollutants, which can really damage your body. So in the short term, you're going to experience coughing, difficulty breathing, allergy-like symptoms. When we were there for a field campaign, my eyes one day during the worst pollution day were crying because there's so much stuff in the air, so you'll experience eye watering, discomfort, just general awfulness. And in the long term, so the people who live there full time, you're going to be more likely to experience strokes, cardiovascular disease, lung cancer, and other lung diseases, as well as type 2 diabetes. So we want to mitigate exposure to these pollutants because they're not good to breathe. So the first question we need to answer in this kind of overarching pollution problem is, what causes these pollution events? And I was being very technical with this diagram. We have a PM 2.5 pollution recipe. And for the Salt Lake Valley, we need to map some topography, some primary pollutant source, and an atmospheric inversion. And we do some air quality, or some atmospheric chemistry, and we get a pollution event. And of course, I'll be a little bit more technical. So our first ingredient, the mountainous topography, is pretty easy to see. It's built within a mountain basin, the city itself, which in the West a lot of people tend to do. Don't know why. The second part is we need some primary pollutant source. A primary pollutant is just a pollutant source directly emitted from somewhere. We can track it pretty easily. And some pollutants common to the Salt Lake Valley are industrial and vehicular emissions, which can lead to NOx. Urban sources are kind of a mishmash of a little bit of everything, but some include PM 2.5 as a primary pollutant emission, NOx, organics, and a lot more. And then the last and kind of niche one to this area is ammonia, which is emitted from agriculture and animal husbandry. And they think, this is not a known thing right now, that mink farming is the largest source of ammonia within this valley. We don't really know. That is the thought. Is it confirmed? Not really. The third thing that we need to drive this pollution chemistry is an atmospheric inversion. This occurs when cold air is present at the ground level and it's trapped in the mountain basin by warm air aloft. These events basically trap in pollutants in the valley and jumpstart a lot of the chemistry that we're going to discuss. But it's a little bit more complex than that initially. In the daytime, the height of the inversion will increase, in the nighttime it will decrease. And where all of the atmospheric chemistry I'm going to talk about in the next few minutes occurs in this kind of nighttime residual area. This is just the difference between the daytime and the nighttime inversion layer height, and it's a little bit less polluted there, which can allow the chemistry that we're going to talk about to occur. So let's zoom in on this residual layer. And this is the part that I would recommend people stop me at if anything is unclear, because this is very chem heavy. I'm apologizing in advance for that. The first part, and if you took gases class, you should know this, is the NOx cycle. This is just converting NO to NO2 in the nighttime, and then NO2 back to NO in the daytime. The primary fuel for this, in this case, would be industrial or vehicular emissions, which we have a lot of in the United States. One part of this puzzle can be that a peroxy radical will react with NO2, usually in the nighttime, to form nitric acid. Nitric acid will then react with ammonia from minks, to form ammonium nitrate. Ammonium nitrate is this main pollutant source and accumulates on existing aerosol and kind of runs out of control and leads to huge pollution events. But there's one issue, and this is really niche to atmospheric chemists. The peroxy radical isn't really around in the winter, so it's not going to do a great job of explaining the wintertime pollution events. It requires some warm air and especially a lot of daytime to form the peroxy radical. There's this third path, which is even funkier. NO2 can react with ozone to form this compound called NO3, which is really unstable and really annoying and will not form at the ground level because there's too many car emissions. But in the nighttime residual layer, which is a little bit cleaner, has a little bit less impact from car emissions, we can get ammonium or NO3 to begin to form. And what will happen is NO3 will react in equilibrium with excess NO2. I know, a lot of N's. To form N2O5. And N2O5 is the star of the show. It's in the title of the presentation. Please keep this chemical in mind as we go through the rest of this presentation. What can happen is N2O5 will react with an existing aerosol, such as the primary sources below. This can include mineral dust, road salt, residential wood burning, and all of these will react differently depending on the chemical composition of the aerosol source. And the rate at which N2O5 reacts with the surface of the aerosol is denoted as gamma N2O5, or the reactive uptake coefficient. And just for an example, if we have a gamma value of 0.03, that means that upon a collision with an aerosol, there's about 3% chance that the N2O5 will actually react and not go back into the gas phase. And once again, this value is very, very dependent on the chemical composition of the aerosol. If we get a reaction, two other pathways are likely to occur in this region. There's also bromine, which I'm not going to talk about because we didn't observe it in our chemistry. The first path is nitric acid, where it reacts with ammonia from makes to form ammonium nitrate, and PM goes up. The second outcome can be if aqueous chloride is present. Chloride is found in salt. So if you have a salty aerosol, ClNO2 can be produced. And the percent of ClNO produced to N2O5 reacted is denoted as the yield of ClNO2 or phi ClNO2, which we'll see that variable come up quite a bit. ClNO2, once again, does some more atmospheric chemistry. In the daytime, it will photolyze to produce a chloride radical. The chlorine radical will then refeed into ozone production, VOC reactions to form that RO2 variable over there, and jumpstart more atmospheric chemistry, and NO2 will refeed into the Knox cycle, once again propagating this reaction mechanism, driving chemistry forward. So if we get ammonium nitrate production, we'll get PM 2.5, and if we get ClNO2 production, we'll feed more PM 2.5 formation. So both are not ideal, but they both react a little bit differently in the atmosphere. And the most important part, and the reason why I just went on this long tangent about this chemical mechanism, is that it's thought that up to 80% of the PM 2.5 formation in the Salt Lake Valley is due to this gamma N2O5 reaction pathway. So for us to understand the PM 2.5 problem, we really need to constrain this variable right here. So just to kind of wrap up this section, I know it was a lot. I'm going to take a quick breath, think about it. The main takeaways are N2O5 will react with existing aerosol in the atmosphere to produce ammonium nitrate. This mechanism is likely to happen in the residual layer of the inversion because at the surface NO is high, which will inhibit the formation of NO3. Not as important, but still important. N2O5 aerosol reactions do account for up to 80% of the wintertime PM 2.5 problem. And to understand this formation mechanism, we need to constrain this gamma N2O5 value. So I'm going to take a second. Is there anything that seems unclear? And it's okay if it does. Okay. I used to be a teacher, so this is my teacher moment. So now I got to answer the question. We did a lot of chemistry. It's a lot of kind of nonsense, if you think about it for a second, until we discuss how we measure it. And this, if you are friends with me and have sat with me at lunch before, have heard of the term flow tube. This is the flow tube setup. What we do is we generate our particle somehow. There are two methods. I'll talk about them on the next slide that I use. We condition the relative humidity to atmospheric relevant humidities because our N2O5 reactions can be dependent on humidity as the chemical composition of the aerosol or phase will change a little bit. We need to add N2O5 artificially into the flow tube. And the flow tube is basically this constrained region where we know about how much time the aerosol and the gas will sit in for. And then we can do some gas analysis as well as some particle surface area concentration analysis using an aerodynamic particle sizer or scanning mobility particle sizer. And then we do this math over here, which I'm not going to go too deeply into, but this is how we figure it out. The second part we need to do is figure out how to generate our aerosol. And the reason that we care about aerosol generation techniques is that aerosol will be generated differently in nature, right? So we want to try and replicate that the best we can in laboratory studies. So there's two methods I've employed over the past 4 years. The first is this custom dry generation mechanism that we use for dust studies. This was made in-house by Drew Mitru, who was here a while back. And what it does is it basically shakes around the dust and adds a clean air into the little flask down here. And that will generate dust, matching normal saltation processes you might see in the real world. Then we dilute it to have a constant surface area concentration generated. And then finally, we add it to the flow tube after some other things to make sure we don't lose too much. The second method, and this one's a little bit more common in our field, is atomization. This is a wet generation process. So we generate our aerosols wet, and then we dry them up in the flow tube, or before the flow tube. And what we do is we take our sample, dissolve it in solution, we'll suck it into this straw, and it'll go into this little mechanism here that then generates our aerosol at a humidity of about 100%. Then we have to analyze the gas component, so N2O5 and ClNO2. And to do this, we use a technique called chemical ionization mass spectrometry, which this mechanism is not identical to what we use, but it's close enough and I didn't want to build one. be real for that. Where what we do is we inhale our gases from the flow tube, and we look for differences in N2O5 and ClNO2 concentrations as we add or remove our aerosol. How this works is it takes the little ionized gas, which we ionize in the IMR chamber, it centers it really well, and then it will filter out anything except for the chemical of interest, which is done using some physical equations, which I cannot derive to save my life, and I don't think anyone else can, except for one guy named Matu. We then detect it using an electron multiplier and get a signal out. And then we also want to look at the chemical composition of our aerosol, because this can affect our reactive uptake coefficient. And there's two methods that I employ that I'll discuss throughout the study. The first one is soluble ion extraction, which I've used for all my studies. We have a filter or sample, we add it into water, we sonicate it in millicube water for 60 degrees Celsius for about 75 minutes to extract soluble ions from the filter source. We then chill it to room temperature for about 4 hours, and then we extract using just a syringe filter. So we just have the millicube water plus whatever ions are in it, and then we'll analyze it using ion chromatography. The second method, which we've used for one study, which we'll talk about next, is single particle aerosol mass spectrometry, or ATOF-MS, depending on what lab you're coming from. And what this does is it will inhale an aerosol, either from the atmosphere, or in our case, the flow tube. It will center them real nice, it will size it for us, and then we'll shoot it with a laser, which will desorb and ionize the chemicals on the particle, which then we can look at the individual ions in both positive and the negative spectra based off of how long it takes for them to fly through that little bottom square at the bottom. So very quick and dirty explanation of those techniques. And then finally, we want to make sure this technique works, because we need to, this flow tube stuff is kind of crazy, right? So what we do is we calibrate our system by using a sodium chloride standard. It's well known in the field that sodium chloride has an uptake coefficient of 0.03 and a yield of ClNO2 of about 1. So what we do is we generate that using an atomization process or a dry generation process. We put it into the flow tube, and then we put it into the flow tube at a bunch of different surface area concentrations. This is because we want to make sure our gamma variable is independent of the size of the aerosol to the best of our ability. So here's an example plot that when I sent it to Cassie, she got really excited because that's a good version of the plot. When you're learning this technique, there's a lot of bad versions of the plot. And all of that is to now inform the next 20 or so minutes of this talk and what I did with all the techniques I just discussed to understand the gamma N2O5 chemical mechanism. So this is the first part. We're going to talk about laboratory studies done at the University of Miami in Cassie's lab using the smaller flow tube. And what we did is we took aerosol sources relevant to the Salt Lake Valley, that being mineral dust and road salt, and we ran them through the flow tube under different conditions. The first part I'm going to talk about, and if you've been to my compasses in the past, you would have seen, is how we quantified playa dust from the Great Salt Lake and its halogen-producing ability. For a little bit of background, I want to give some background on the Great Salt Lake, is that over the past 40 or so years, the Great Salt Lake has been shrinking at a very alarming rate. This is mainly due to climate change as well as water practice misuse. And that little kind of red area outlined, that's how much the lake has shrunk in the past 40 years. And what can happen is it will expose this playa dust, which is really susceptible to being lofted into the atmosphere with wind, and lumped into the atmosphere. And by the way, Salt Lake City, relevant to the Great Salt Lake, is right here. So very close. And in the evening, it can participate in the chemistry we just discussed, right? We'll have our NOx source, it'll become N2O5 in the nighttime, it will react with the playa dust, with the likelihood of that gamma variable we talked about, and it will produce ClNO2 or nitric acid, depending on the yield variable that we measured. And this study has been done once before by Drew Mitri, the guy who made the dry gen setup. He took one sample from the southern region of the Great Salt Lake and noticed it's not very reactive. It's about a less than 1% likelihood that N2O5 would react with playa dust if it was lofted into the atmosphere and put into the Salt Lake Valley. Though it was very, very good at forming ClNO2, basically a near unity chance that would happen. But there's a lot of lake, and there's also this weird discoloration very immediately noticeable between the northern and southern areas of the Great Salt Lake. This was actually due to a causeway that was put in place about, I think, 60-odd years ago that limited mixing of water between the northern and southern regions. And the southern area of the lake has all the water inputs, while the northern region has no water input. So it's basically drying a little bit faster. And that's just resulted in a salinity that's about 3 times that of the southern region's water, which is pretty nuts. But this got us thinking, well, do differences in water salinity affect playa mineralogy, or the chemical composition of the aerosol, and how do these differences affect our uptake and yield coefficient? So what we did is we karate chopped the lake in half. Blue will be northern region samples, red will be southern region samples. We took 4 samples from each part of the lake, and we ran them through the flow tube. And immediately you noticed that the reactivity of playa dust is heterogeneous. It's different between different parts of the lake. Between the northern and southern region, the northern region is about twice as reactive with N2O5, meaning that about 4% of any N2O5 that comes in contact with the playa dust aerosol will react, while the southern region is about half as reactive, meaning about 2%. And in this little corner, near where Drew had his sample, we see a similar reactivity. So it's not like Drew's reaction rate was wrong, it was just very location dependent. But what's causing differences in these reaction rates? That's what we wanted to probe a little bit more. We can see the most reactive sample, Na1, which is from the way northern part of the lake, and the least reactive sample, Sa4, which is from the least reactive part of the lake, in their single particle mass spectra. And what we did is we just took the relative abundance of individual ions and then did a subtraction plot. And immediately we noticed that silicates and chlorides are a lot more abundant in the northern region. Those chemicals have been previously spoken to or are shown to be a lot more reactive than other aerosol types, while organics are more abundant in the southern area of the lake. It's a little bit funky. Organics are known to not react with N2O5 that much. It will not get back into the gas phase, and not much chemistry will happen. So we did a little bit more digging into this question, and what we did is we plotted the reactive compounds over the unreactive compounds. And a pretty neat linear correlation has been noticed. And these are field samples, right? You're not going to get an R squared of 0.99, but a correlation of 0.7 is pretty good for this region, suggesting that the increase in chloride and abundance of silicates in the northern region are likely enhancing the N2O5 reaction rate, while the increase in organics in the southern region, or the relative abundance in the southern region, is likely inhibiting that N2O5 reaction. So now we wanted to put kind of a more broader impact or broader picture on this, which is, does the Great Salt Lake contribute to the ClNO2 production? Because the yield is near unity the entire time. Does it contribute to this pollution mechanism in any significant way? So we did this kind of back of the hand calculation or parameterization, where you said the gamma and yield, values that we collect during the study, times ambient concentrations of N2O5 times the surface area equals the production of ClNO2. We took the average uptake coefficient of all the samples in this study, just to be a little bit non-biased. We took surface area concentration measurements from the UWFPS campaign, which was done by NOAA to test wintertime PM2.5 formation in the Salt Lake Valley. So this was taken in the residual layer, which is really great for us. And then we assumed a few N2O5 concentrations based off of literature. So most of these were under clean and polluted conditions, and can kind of inform what we might see for N2O5 concentrations in the ambient air and the residual layer. And we got this plot, and it's not easy to read, so I'm just going to summarize it. About 5% of the ambient ClNO2 observed during the UWFPS campaign can be attributed to playa dust wafted from the Great Salt Lake, based off of our back-of-hand calculations. This was not a crazy computational model. This was just an inquiry that can inform more thorough studies in the future. Though we also want to know that wintertime is generally a low dust season for this region. That's mainly because snow will cover the lake. If there's snow on top of a playa bed, it's not going to be wafted by wind, and the winds are also a little bit weaker under the wintertime. However, in the springtime especially, during tax day, which if you haven't done those, you might want to do them, you'll hear about the legendary tax day dust event where the whole city gets clofted and playa dust from the Great Salt Lake and other desert dust regions, as well as the summer where winds are a little bit higher. So we do expect a higher contribution of dust to ClNO2 production depending on the time of year. Which is to very quickly wrap up this part of my work, means that In the northern part of the lake, where silicates and chloride are a little bit more dominant, the reactivity of the playa dust will increase, leading to more PM 2.5 production or ozone production, while in the southern region, where we have a little bit more organics living in our playa dust, the reaction rate will be inhibited, likely reducing the impact that playa dust can have on secondary particulate matter formation, which is a step into understanding their pollution problems within the Salt Lake Valley. The second part of dirt-type sources that I quantified during my time here is road salts. So if you live in the northern region of the country, which almost none of us do except for Gelby, she's from New York, we know that right before a snow event, they'll usually coat the roads in road salt. This is basically to protect the roads from freezing over, more safe for cars, less fatalities and injuries. And what they do is right before the snow comes, they'll coat the roads in road dust. The snow will appear, and it'll keep the roads from freezing over so that people can get to work, do their jobs, and not get hurt. And as the snow begins to melt, the road salts will be dissolved in liquid water, which will live on the roads, and that spray can easily be aerosolized by the mechanical movements of cars. And as that continues, we'll just notice an observed amount of aerosol chloride. This was done in Ann Arbor, Michigan, at a study in Carrie Pratt's lab, where they found generally aerosol chloride increases after a snow event, likely due to road salts. And as this continues, over and over and over again, we'll have a lot of aerosol chloride in the air, which can participate, once again, in this reaction mechanism, where N2O5 will react with an existing aerosol to produce ClNO2. And so what we wanted to do is, in the laboratory, take a few different types of road salts from around the country. We started with road salts from Salt Lake City. They're pretty simple. They just have salt, as well as Ann Arbor, Michigan, and Lynn, Massachusetts. The other two were mainly a proximity thing because they're easier for us to get. We also took a sand-salt mixture. In some parts of the country, they'll put sand in the road salts to increase vehicle traction and allow cars to drive on the road a little bit better. This is done a lot in Massachusetts. And what we did is we got one sample directly from the Department of Public Works. And then one day, while I was on an Aerodyne visit, I walked outside with a shovel and was shoveling road salts into a bag for my carry-on. Science. The last part of this puzzle is brine solutions. Now, brines are used as a pre-road treatment. Right before you put down your road salts, you'll spray the road with brine. And there's two samples that we got. One that's just sodium chloride, calcium chloride, normal salt, and one that contains something called beet juice extract. Now, beet juice extract is known to reduce the freezing point of water. It's also very cheap to buy, so Michigan chooses to mix their brines with beet juice to increase the abundance and lower the cost. And how do road salts react with N2O5? This is what we're publishing right now. It varies a lot depending on sample type and humidity. And this plot kind of brings two big questions up front. First, why does gamma drop when the relative humidity is low? The second is, why are sand salts so reactive? Those guys in green, why are they so reactive? Well, let's answer the first question. Why do we see this drop at low humidities and reactivity? And I just separate all of them out at 20% relative humidity. And for the pure road salts, you can really see that trend. The main reason that we see this drop in humidity is that the pure road salts are mainly made of sodium and chloride, which if you have used table salt or you have that at your house, you do have readily available. The reason why N2O5 does not like reacting with road salt at low humidities is because the chloride, which is usually in the aqueous phase when it reacts, will enter the solid phase below a 40% relative humidity. This basically shuts off the chemistry because there's no chloride for it to react with. So say, where's my chloride? And then like any good party, you'll say, all right, this person's not here, I'm out. But the brine solutions are a little bit funky. Those should be the same salts, right? But they are showing an appreciable reaction rate, about 0.03 at a 20% humidity. And one of them has beet juice. That's organic. It should inhibit the chemistry, right? Well, not quite. They have a lot of calcium, which is that yellow guy up there. And that's indicative of a chemical called calcium chloride. Calcium chloride is hydrophilic, which means it loves water. When it goes to the party and sees a cup of water, it's going to hang out. It means that aqueous chloride will be available at relative humidities as low as 10%, which is really awesome for the science, not great for air quality in that area. And then the second part of this question is, okay, we kind of understand the brine solutions, the road salt. What's up with the sand-salt mixture? And this gets a little bit funky. Those big red lines at the top in the bar plot is indicative of insoluble ions. That means our ion chromatogram could not detect it, which we assume to be some silicate-type compound. Now, silicates are very common in mineral dust, which is what we saw in the Great Salt Lake, and that humidities really like reacting with the surface of N2O5. So values as high as 0.08 have been observed with silicate-containing compounds at low humidities, and mineral dust has been as high as 0.16, so about a 16% chance of a reaction happening. And this matches what we would expect. So if we assume that the chemical compound that is present in the sand is silicates, science would hold true. So to kind of wrap up this shorter section, N2O5 will still react with road salts to produce ClNO2, which can impact air quality. And at these low humidities, the reaction rate is really dependent on the relative humidity, or not the relative humidity, the chemical composition. But as we kind of reach that 40% or higher region, the reaction rate nears unity, everything's about 0.03, and our chemistry continues as expected, which means we can now model it. So now we get to kind of like the piece de resistance of my PhD, and the part that I like telling people about the most, which is directly measuring the N2O5 reaction rate in the Salt Lake Valley. So if we remember this graphic, most of our chemistry is going to occur in this nighttime residual layer. We're not going to see as much in the ground level because N2O5 is non-existent. We're not going to sample up here because there's not as much pollution outside of the inversion. And the question that we wanted to ask is, do our laboratory assumptions of gamma N2O5 match real-world observations within the residual layer? So how do we get up to about 180 meters above the ground level consistently? Well, the University of Utah has a lab over at that height, which is great. So what we did is we took this initial flow tube, which is the glass flow tube in the lab, pretty skinny, pretty dainty, but it's great. It helps us find gamma, easy to calibrate, super easy to clean, right? Well-documented use case. The issue with this small flow tube is that our aerosol only lives in there for about 15 seconds, which means that we can't look at ambient concentrations of aerosol. We have to jack up the surface area concentration to really high quantities. So what we had to do to measure ambient aerosol is build an ambient aerosol kinetic flow tube. Once again, very good at helping us find this gamma N2O5 value for ambient aerosol. And the reaction time is now 8 minutes. That drops the surface area concentration down quite a bit. There's two cons with it. The first one is it has a size cutoff. So anytime there's a particle greater than 1 micron, it's going to disappear. That's mainly due to how the system is built. The other issue is people don't really use it. Why? Because N2O5 sticks to metal. And if you look at the composition of this, it is made out of metal. So it's a pain in the butt to work with. And just to put this into reference, it took about 6 months to build and test and calibrate this before you deployed it into the field. And this is the third one ever built and deployed in the United States, to the best of our knowledge. So not a common technique. And here's kind of our general lab setup. You can see when the field kind of loopiness kicks in. Cassie was very proud of me in that moment. We deployed our ambient flow tube to the HART lab. This is run by Ann Gannett Haller at the University of Utah. We had a really nice cushy lab space about 190 meters above ground level. This was great. We had our ambient flow tube right here. We injected 100 ppt of N2O5, which matches residual layer concentrations quite well. And we also built a custom-built filter manifold, which will turn on and off our aerosol every half hour, as shown in that graph in the top right corner. We deployed a SIMS, an SMPS, and then we also deployed a Moody, which allows us to collect filters every day. This is a very well-known field research institute as well, which means that they're home to a site called MesoWest, which constantly collects ozone data, PM2.5 data, relative humidity, temperature, helps us understand and quantify our chemistry, and it also had a NOx monitor, which helps us QC our data and make sure that our N2O5 is not being destroyed by NO. Awesome. And here's a very, very, very deep and crazy and gross graphic that we're going to break down real quick of the field campaign results. The first part I'm going to mention is the valley heat deficit. This calculation is a back-of-the-hand way to tell when an inversion event's occurring. If the valley heat deficit is above 4.04, which we calculate using potential temperature profiles, we are in an inversion. However, the calculation is a little hand-wavy. Here's a day where we do have an inversion, but the valley heat deficit does not think we have an inversion. Where we can see the residual layer capping our nighttime chemistry. This is where we're sampling. Once again, we're not floating a helicopter, we're in a lab on the side of the mountain. And in the daytime, the inversion once again increases. Now, I just want to note too that that's a different inversion day, but I decided to plot that for some reason. So the VHD can help us identify when an inversion is occurring. And when it's above that line, we're very confident that we're having an inversion event. And when it's below it or nearing it, we do have to quickly look at the radio sounding to see what's going on. The second thing we can use is NOx. As mentioned, NO and NO2 concentrations do increase under inversion events. So we can use this as a proxy to understand atmospheric stability. It's not going to give us a quantitative number. We kind of have to vibe check it. But when we see higher concentrations of NO2 or NO, and usually NO will increase in the daytime, that means we have an inversion. Which kind of allows us to give this atmospheric regime. You're going to notice I'm using the word stable. Usually people in the Salt Lake Valley use the term persistent cold air pool to describe their inversion events. However, like any amazing and beautiful field campaign, when you go to study a specific thing, it's not going to happen. Yep. Danae's my homie today. So, instead we have periods of stability and periods of clean air. And the stable periods occurred at the beginning and ends of the campaign, and in the middle it was mainly clean. At the bottom we have our gamma N2O5 values, which we collected about every hour, and after we QC'd the data, we lost about, I think, 60% of our initial gamma values, which for the ambient flow tube is surprisingly good. And we also have our once daily collected soluble ion filters. So to match the time resolution here, we did go for daily median values of gamma N2O5, just so these look a little bit happier. I don't know, I'm going to shift our perspective a little bit. Take out the valley heat deficit, take out the NOx, I already justified it to you, and instead zoom in on the N2O5 and soluble ion data. I'm also now just going to focus on the relative mass fraction of our soluble ions. And we're going to go through each individual period that we've identified. The first polluted period is pretty straightforward. We have a notable increase in NOx, or NO3, and ammonium, which is indicative of that ammonium nitrate accumulation we discussed earlier, right? We see this blue bar go up, that's NO3. You see this red bar go up, that's ammonium. Under inversion conditions, ammonium is in excess due to our very ammonia-rich minks. Once again, this is the assumption in the Salt Lake Valley. We don't actually know where it comes from. And what we notice, which is really neat, is that as this nitrate increases, our gamma value begins to decrease. And one thing I didn't mention is that N2O5 has a vendetta against NO3. It does not like reacting with NO3, and this is called the aerosol nitrate effect that we're observing. And right here would suggest that as nitrate occurs or accumulates, our PM2.5 production will begin to decrease. Under this clean period in the middle, our gamma values skyrocket. What's going on here? Well, we have a notable increase in calcium and sodium, which might be indicative of mineral dust. We also have nitrate hanging around, but it's pretty low compared to the polluted period, which would suggest that during clean periods, especially when it's dust-rich air, that PM2.5 production would be very high. So when we combine these two data points, and assume that we caught the entire inversion instead of missing part of it because our instrument didn't work, the gamma N2O5 value will begin to decrease as the inversion continues, right? And once again, we see this nitrate increase and this NO3 value begin to decrease. And we're just going to ignore these two data points because nitrate should never be that low. So in the paper we discuss it, but it's a lot. And then finally we have this kind of homogeneous aerosolish type data where we both get clean and polluted conditions. And this is really neat. We see very similar ion data, decent NO3, high sodium and sulfate. That's usually indicative of clean conditions. And this was right after a snow event. suggesting that our aerosol population should have a large contribution of road salts. And once again, that sodium, and there's some fluoride in there as well, would be indicative of the Salt Lake Valley roadsides. And at the beginning of the campaign, it was too hot for ammonium to stick around in the aerosol phase, so low ammonium nitrate, suggesting that this gamma at the end is kind of controlled by Salt Lake City road salts. And outside of this one kind of nutty day, that is honestly probably just error, or a little hallucination, we can see a pretty consistent gamma N2O5 value of about 0.03, which does match the road salt study quite well. So we're going to split this into 3 separate regimes: nitrate dominant, dust dominant, road salt dominant, kind of cleanish polluted period at the end. And when we extract the most important soluble ions that we were discussing here, we can see some pretty interesting correlations begin to occur. As the mass fraction of nitrate begins to increase, our N2O5 reactivity decreases. And for people who do modeling, I'm sorry, but this is a really good correlation for our work. Under clean conditions, when sulfate and calcium are higher, indicative of dust, we begin to see an increase in our gamma value, which would suggest that as pollution events persist, we are likely seeing the accumulation of nitrate inhibit the PM2.5 production in the Salt Lake Valley. Now that's kind of hand-wavy. Okay, so what? Well, right now I'm working with the wonderful Professor Siyuan Wang in the back of the room to begin modeling this within kind of a faux Salt Lake Valley area. Right here we're beginning to form N2O5 within the inversion, which is kind of indicative of where our inversion is. We're starting to model this heterogeneous chemistry. Now I will note, these are like the 3rd set of plots that we've made so far. So this area is still very preliminary, but in the next few weeks we should be able to wrap this up and really understand if nitrate's controlling this PM2.5 production in the Salt Lake Valley, or if it's something else. So there's a lot of chemistry. I apologize for that, I am a chemist. I'd like to wrap up by thanking the amazing collaborators who've helped with this, as well as Noah for funding this project, and I will happily take any questions.
Thank you, Jake. Thank you, James. Does anyone have any questions for James?
Thanks for setting a high expectation for us chemists, James. Would you mind going through, it was one of the last things you talked about where it was about the composition, and I'm wondering if this different, I think the slide before where you had the bar graphs of what, yeah. So is that dominance of dust or nitrate or road salt, is that based on like loft events, or how is the composition changing within just 2 weeks' time?
Well the nitrate's pretty, so this is relative abundance. So as PM2.5 accumulates, ammonium nitrate will take over most of the time. So this is like 30 microgram per meter cubed ambient aerosol. This is like 2 microgram per meter cubed ambient aerosol, which honestly this plot shows a little bit better. Right here. So here's the total mass fraction rate. So we did not have a really, really great single particle way to quantify these aerosol, which meant that we were reliant on these bulk chemical techniques, which take all of the aerosol types and put them into one homogeneous mess, and we assume or hope that what's in there is soluble. Which means we're kind of basing it off of previous studies in the area where they've attributed different kind of relative abundances of these constituents to aerosol type. So it's a little bit hand-wavy.
Cool, thanks.
Yeah, though single particle data that we are processing did show some dust, which is good.
Any other questions in the room? Are there any questions on Zoom? Oh, maybe so.
I got something on Zoom about mink farms. What kind of filtration system, if any, does mink farm have effect for aerosol versus, groundwater contaminants? I don't know a lot about groundwater, but I do read the Salt Lake Valley News because I really care about their data. The Great Salt Lake is contaminated by runoff. I don't know if that's agricultural mainly. There's a lot of different industry. They don't have any filtration system for the aerosol, I would guess, because it's kind of animal husbandry. I don't know if they can capture the ammonia. The kind of nutty part about mink farming is people are trying to attribute this ammonium source, and there's this one mobile campaign done that kind of drove around, and near mink farms they saw high ammonia, and everyone said, all right, it's mink farming. So to really understand this ammonia source, and if it is mink farming, a more thorough field campaign would have to be done with ammonium attribution, which has not been done yet. But they use DAC bill, which is their Department of Air Quality. So I don't think they use filtration for their aerosol. I hope that they use it for their groundwater, but I'm not sure. So a non-answer there.
Looks as if Joe Prospero may want to say something.
Yes, a very nice presentation, James. I mean, this is as you mentioned, this is sort of in a basin. Where does the aerosol go? I mean, you're talking about these multi-days of sampling, but how much of an exchange is there out of or transport out of the basin or indeed into the basin? Are you following the aerosol mass history?
Yeah, it's a tricky question because it's such a fine resolution that a lot of transport models can't capture that. Under non-inversion conditions, we're a lot more likely to see exchanges out of the mountain just over the ridge. When the inversion happens, we know that the NOx is trapped, and we can track that with the ammonium nitrate buildup. There's also, it's kind of like a U shape for the basin itself, so you can get transport in towards the airport area. But a lot of the industry is also localized, so a lot of the emissions are just happening within the basin. So transport in and out of the basin, I can't speak to quantitatively. But when the washing out happens, it's usually due to a clean air coming in and diluting the aerosol. So it's probably more of a depositional process, would be my guess. But I would have to look into it a little bit more.
Good, thanks.
We have a question in the room.
Would you be able to touch on again why the production of NO3 makes it so N2O5 doesn't like to react as much?
Yeah, this is going to be quizzing me on something I should have memorized. So the aerosol nitrate effect, when N2O5 touches an aerosol, right, it'll go in with the N2O5, and then it will go through a dissolution reaction where it's really NO3 minus plus NO2, and there's kind of two pathways. It can re-exit into the gas phase, or it can choose to react with something such as chloride to go form into Cl, and I think it's something like this, which will then go out into ClNO2. Don't take this chemistry as gospel. Or it can react with some liquid water, I think, and then become nitric acid. When there is an abundance of nitrate in the aerosol, the equilibrium of the chemistry within the aerosol will shift back towards N2O5. So it's just shifting the equilibrium from NO3, NO2 dissolution back to NO2O5, which I think I kind of botched, but that's the general idea.
Oh, you have quite a few more questions, actually.
Oh, no.
James, awesome job. I was curious on your interpolation to aircraft data, I think it was.
Oh,
maybe
yeah.
You took the rate. Can you speculate on, it looked like maybe it was an overestimation of where I put the yellow versus green.
Was it this part?
No, it was earlier. I think you took the rate constants and then applied them to...
Oh, the ClNO2 data.
Yeah.
Right, okay. So this side, I didn't explain this plot at all because it's a little bit beefy.
Mm-hmm.
The observed ClNO2 is in green, and then this is the observed surface area concentration, which is that purple variable up there. So we didn't overpredict ClNO2 in our parameterization at all.
Oh, okay.
Yeah. And this was once again kind of like a hand wavy back of the hand calculation showing that it's likely important to this mechanism in the Salt Lake Valley.
Oh, okay.
Yeah.
Thank you.
Just kind of go around the back here.
Save the best for last with Cassie.
Great talk, James. I was wondering, in your dust samples, do you see any like irons or transition metals, that kind of spicy stuff?
I'm going to ask a question to Cassie. I don't think the Sims can't really, or the ATOP can't really look at iron, right? Or can? Then no, we didn't see a lot of iron.
The 56 could be iron.
Yeah. We attributed it to calcium, oxygen, but it could be iron. We didn't do any like metal explicit analysis on it, but for that chloride mechanism that we're thinking about could be important. There's a methane equilibrium discussion about iron transition state chemistry that a lot of atmospheric chemists are beginning to think about, and I think that's what C1 was probing. But I didn't do a transition state test with iron, so I'm not sure. But maybe.
All right, and Cassie?
So Sion, if you're interested in that, you should chat with James. So he's going to look at our year of Barbados data of iron and chloride. Yeah. That was, yeah. Okay, that's only spicy for him. So getting back to the motivation of the whole thesis, like, what should we do about these air quality issues? Should we be thinking about water management practices, road salts? Should we be mad at the fashion industry and their use of mink? I know. The whole thing about minks is sad.
I know. Well, and it's kind of, I was talking to Gannett about the minks, and I just find it hilarious that that's what we assume. I think we have to look at the limiting reagent in this PM 2.5 production. And in my opinion, and the car drivers and industry people are going to hate me, I think the NOx might be the issue here. The N2O5 mechanism is driving a lot of this chemistry, but the N2O5 is forced from car and industrial emissions. I think it's probably better practices on reducing vehicular emissions, which the Salt Lake Valley is actively doing, which is great. So they started the TRACS program, which is electric buses and trains to help people around the city. They have incentives for during pollution events to reduce, NOx emissions. So they're doing an amazing job. And I would say probably the best way to reduce pollution is to reduce NOx. The N2O5 is just getting into the modeling behind it.
All right, so we'll keep making those mink coats then.
I mean, I'm not gonna buy a mink coat, but enough people. It depends. On clean conditions, ammonia can be a limiting reagent in that chemical mechanism. I just don't know the sensitivity to it. I think some sensitivities tests to that like transition point between ammonium and NOx limited would probably be to the benefit of the PM 2.5 production equation people.
Yeah. Why don't we know the ammonium well enough?
It's just kind of hard to sample.
Yeah.
All right, if there aren't any more questions in the room. Oh, there are?
I don't know, but Joel has his camera on.
Oh, okay.
Mm-hmm.
I have one more question.
Mm-hmm.
If NO2 is so important, have you looked at the weekday, weekend changes in NO2 concentration and the consequences of that?
Mm-hmm. Haley Humble and John Lynn's group just published an amazing paper on that. So I haven't read it thoroughly, but this is a large topic within the Valley. The chemistry has not been probed because we didn't see high enough differences to affect the N2O5 mechanism. But she was mainly looking at source apportionment. So that question can be answered. Do I know the answer off the top of my head? No.
Oh, okay.
But I think once again, it's towards more NOx regulation.
Yeah, but you would think that if traffic and industrial processes are responsible for most of the NO2, you would think you would see such change.
Right, yeah. So that's Haley's paper, and also a lot of work out of John Lynn's group does probe that, and there should, I'll have to reread the paper to say quantitatively, there should be a reduction in NOx observed during the weekend.
Well, send the PDF to me when you get it.
Perfect, yeah. And within our study, we did notice diurnal variability in NOx concentrations as well. So like during peak traffic hours, we couldn't sample because the NO was too high for us to run the flow tube.
Yeah.
So there is variability. I just can't speak to like the year-long quantitative variability, but I'll send you some papers from John Lynn's group on it. His work is great.
All right, well, if there aren't any more questions, then let's give James a round of applause. Thank you, James.